all and welcome to the Chemistry 111 TED Talk and explanation video of the preparation and analysis of potassium trioxylatoroferrate 3 trihydrate crystals, also known as our green crystals for our green crystal lab. In order to be successful for this experiment, we're going to require a few key pieces of equipment. Some of the most important of this equipment includes a buchner funnel, a flask, paper filters, a hot plate, an ice bath, 2 graduated cylinders, 2 beakers, and a specific amount of potassium oxalate hydrate, and some iron 3 chloride. These are not all the pieces of equipment we need, but these are some of the most important. For the rest of the equipment list, you can look in your lab notebook. Before we can really begin our experiment, we should review the topics that we're about to cover. So today we'll be doing a recrystallization in order to produce potassium peroxide crystals for the second and analysis part of our experiment. So recrystallization, what is that? Recrystallization is the process that is used for purifying an impure compound in a solution. This process relies heavily on the differences in solubility between the product and the impurities. And it relies on the varying solubility of the product at different temperatures. The best type of solvent is going to be one in which you have the impurities are very soluble at all temperatures, while the compound of interest, our crystals, will only be soluble at low temperatures. Now that we have a general understanding of what's going on in this experiment and we know what equipment we're going to use, let's just dive right in. I'm only be covering the key points of this experiment, offering some explanation and analysis, so please follow along in your lab notebooks. The first thing we're going to be doing is forming our solution. To form this solution, we're going to take 20 milliliters of DI water and a potassium oxalate hydrate and combine this in a beaker. Once we have this in a beaker, we're going to place this beaker on a hot plate at medium heat and heat until all the solids have dissolved and formed a solution. Once we let this sit for a while, we can then prepare our iron 3 chloride. Once we have our measured amount of iron 3 chloride ready, quickly remove your solution from the heat and place in the iron 3 chloride. Then let this sit on a ceramic mat until it's at room temperature. Once at room temperature, we can then place our new solution into an ice bath to cool. After about 15 minutes, there should be a green precipitate on the bottom of the beaker. So, what's happening in this experiment is a reaction between the iron 3 chloride and the potassium oxalate that will yield our green crystals. In the preparation of our green crystals, we are essentially utilizing the heating and cooling of the solution to separate out and then precipitate our crystals. The first thing we're doing is by heating the solution is separating out our crystals from the impurities. Then, by putting in the ice bath, it's allowing our crystals to form a precipitate on the very bottom of the beaker. At this point in the experiment, you should have a precipitate in the bottom of your beaker that is mostly comprised of the green crystals. But we can't be sure that this is 100% pure. So what do? We perform a purification. Purification is essentially just repeating the process of heating and cooling our solution in order to get off any other impurities that might have stuck around from the first time. Once we've done this, we can then pour our solution precipitate through gravity filtration to remove the water and have an end result of just our green crystals. But gravity filtration is essentially when we're using gravity to pull water through a filter and just remove the water. Pretty simple. Once we've done this, we should have the end product of our green crystals. So now that we've actually gotten our green crystals, let's analyze them. To do this, we'll be utilizing different types of titration to analyze the chemical formula of our substance. A titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. Typically, the titrant, which is a known solution, will be added from a burette into a known quantity of the analyte, which is going to be the unknown solution. Knowing this volume of the titrant added allows a determination of the concentration of the unknown. Often, an indicator, in our case potassium permanganate, is used to signal the end of the reaction or the end point. So the first titration method we're going to be covering will be the titration of an oxidation-reduction reaction to determine the percent value of the oxalate ion in our crystals. An oxidation-reduction reaction is a reaction that involves the transfer of electrons between two species. Or it is any chemical reaction in which the oxidation number of a molecule, atom, or ion change by gaining or losing an electron. So what's happening in this oxidation reduction reaction that should be floating above me is the carbon in the oxalate is actually getting oxidized and is losing 1 electron during the reaction, while the manganese is getting reduced and is actually gaining 5 electrons. So that is why it's an oxidation reduction reaction. So if you finish your titration, you're probably thinking to yourself, now what? How do I determine the percent of the oxalate in the crystals? Well, unfortunately, you gotta do a lot of math. To determine the percent composition of the oxalate ion in the green crystals, we're gonna have to do a decent amount of math. The first thing we're gonna do is determine the moles of potassium permanganate used. This is a relatively simple thing. All we're gonna have to do is take the volume and multiply by the molarity. So the volume in liters of my potassium permanganate used was 0.0322. Then I have to multiply it by the molarity of the potassium permanganate, which is on the bottle, as 0.01. And I will get 0.000322 moles, or 3.22 times 10 to the power of -4 moles. So the next step in finding the percent of oxalate used is going to be determining the moles of oxalate using stoichiometry. At first, stoichiometry can be pretty intimidating, but once you get it down, it's not that bad. The first thing I'm going to do is take my moles of potassium permanganate used, put it right here. Then I'm going to multiply this. by the molar ratio of potassium permanganate and oxalate to find the moles of oxalate used. And by doing some quick multiplication, you can see that the moles of oxalate used will be 8.05 times 10 to the -4th moles. Pretty easy, right? Then next step is to find the mass of oxalate in the sample. Once again, really easy. All you have to do is take the number you just found, 8.05 times 10 to the -4th, and multiply this by the molar mass of the oxalate ion, which, if you look it up really quick, will be 88.02 grams per mole. And once again, plugging this in our calculator, you can very easily find that this will be 0.071 grams of oxalate in the sample. Now that we found the actual mass of the oxalate in the sample, all we have to do is divide that by the actual sample weight to find the percentage. So 0.071 grams divided by the initial sample of our green crystals that we use in this experiment. For me, this is going to be 0.129 and will give me 0.55, and then I have to times this by 100 to get 55% composition of the oxalate ion in the sample. Alrighty, what we can do next is determine the actual percentage of oxalate in the green crystals. So what we can do is determine the molar mass of each compound. All you really have to do is add up the atomic weights. And I went ahead and did this, and for the oxalate, I got 264.06 grams per mole. And for the entirety of this green crystals, I got 491.25. To determine the actual percentage, as you could guess, divide 264.06 by 491.25 to get 0.537, or 53.7%. Alrighty, and the last thing we can do is quickly calculate the percent error. Already, and the last thing we can do is quickly calculate the percent error of our experiment. To do this, all you have to do is multiply the actual percentage by our experimental and then divide by the actual. And if we do this, we can see 0.537 minus 0.55 all divided by 0.537 to get a percent error of 0.024 or 2.4% error. In the next part of our experiment, we will be determining the amount of iron in our green crystals. To do this, we will be using a precipitation reaction and a titration curve. So a precipitation reaction is the formation of an insoluble salt when two solutions containing soluble salts are combined. The insoluble salt that falls out of this solution is known as a precipitate, hence the reaction's name. And a titration curve is a plot showing the change in pH of a solution in a flask as the reactant is added from the burette. To actually do this precipitation reaction, we are going to make a solution of our green crystals and distilled water in a beaker. After we made this solution, we're going to place it under our titration apparatus, where we'll be intermittently adding small amounts of sodium hydroxide. The sodium hydroxide reacts with the green crystals and forms iron 3 hydroxide. In addition, we also have the lab press machine measuring the pH levels of the solution to see when the actual reaction is stopped. What we'll see is on our graph. We'll go from here and spike up. This will be the end point when it's wrapped. So once we fully completed our titration, we'll actually be able to determine the percent composition of iron in the green crystals. But unfortunately, as you might have guessed, it's going to take a little bit of math. All right, now we're going to determine the amount of iron in the actual green crystals. The first thing we have to do in determining this is find the moles of sodium hydroxide used. So all our numbers are obviously going to vary because we're doing two different experiments, but for me, I utilized 34.8 milliliters of sodium hydroxide. To determine the amount of moles used, all I have to do is times this number, change this number to liters, which would be 0.0348 times the molarity, which is 0.1, to get 0.00348 moles of NaOH used. Next step is just going to find the moles of iron 3 chloride. And once again, we have to use stoichiometry, but since we've done it before, we should have a better understanding of it. So we're going to take the moles of NaOH, and then we're going to find the stoichiometric ratio of iron 3 chloride to NaOH, which is going to be 3:1. And then we just do some simple multiplication to get 0.00116 moles of iron reacted. Alrighty, the next step is going to be to find the moles of Fe3+ reacted in the reaction. So to do this, we're going to use the titration curve that we got back during the experiment. It might be hard to find on the experiment, but your number should show a specific point where it upticks significantly. For me, that was 11.2 milliliters of NaOH. So all we have to do to find the Fe3 reacted is take this in liters, which is going to be 0.00112 moles of NaOH. And once again, the stoichiometric ratio of NaOH to, this time, Fe3+. We will get 0.00037 moles. And then we find the amount in grams that were used, which is really, really easy. All you take is the molar mass of Fe3+, multiply that by the amount of moles we had in our experiment to get 0.021 grams used. Then the last part is to actually find the real percent composition, the R percent composition of the iron in the crystals, which is going to be 0.21 divided by the total amount we added, which is 1.163, to get 127 or 12.7%. The last and final step is going to be finding the actual percentage of Fe3 plus in the green crystals, and then the percent error. Just like last time, all we have to do is find the molar mass of Fe3 plus, which is going to be 55.85, and the molar mass of the crystals, which is 491.26, which I'm going to label as GC or green crystals. Then we divide 55.85, by the total molar mass to get 0.1136 or 11.36% of iron in the green crystals. To finish her off, all we gotta do is take 0.127, subtract the actual value of 0.1136, divide it, multiply by 100 to get our percent error of 11.8%. Not bad, all things considered. And with that, we are done with the experiment. Hopefully, my little TED Talk and explanation helped to give you a little more understanding of what you're actually doing in this experiment, what's going on, and what concepts apply to it. Thank you all for watching, and have a great day.